So today we will discuss about the structure of an electrified interface. First of all, why we are considered about electrified interface or electrical double layer is due to the fact that the separation of electrical charges occurring at the interface due to the formation of electrical double layer can be used to study the interfacial capacitance, that is termed as electrochemical double layer capacitance in supercapacitors. These electrochemical double layer based supercapacitors have certain advantages over the conventional energy storage devices like batteries or fuel cells. The study of electrical double layer is also used in various other applications, like in order to explain the stability of the colloids. They are also used to explain the deposition process occurring at the surface of metal involving the redox reaction. Now, first of all, what is an electrified interface? It is a physical boundary that is developed between two dissimilar phases is known as electrified interface. For example, when a metal electrode is placed in an electrolyte solution, due to the difference in the phases, interface region is developed. As we know that almost all the surfaces carry excess of electric charge, either positive or negative. So, as shown here, excess of positive charge on the surface of electrode. So, due to this, this interfacial region becomes electrified. Uh, and develops a electric field or an electric potential. For example, as shown here, when an electrode is dipped in a solution of an electrolyte, due to the excess of positive charge present in the electrolyte, it will draw out the positively charged ions of the solution, thus giving rise to an interfacial boundary which is electrified in nature. Why the bulk region is different from the interfacial region. The breakdown of electroneutrality occurs at the surface of electrode and electrolyte interface because near the surface of the electrode, the forces experienced by ions and molecules of solvents are not isotropic or homogeneous in nature. So there is a perturbation in the uniform properties of the interface region and give rise to net orientation of the solvent dipoles at the electrolyte side of the boundary. As shown here, an electric field is generated and when the molecule or a lamina is placed inside an electrolyte, it experiences an equal and opposite amount of force in all the direction. So it is isotropic in nature, and the electrolyte or the bulk solution becomes electroneutral and does not give rise to any net electric field or a potential. While while in the interface region, at this region, the forces experienced by the ions or the molecules of the solvent or an electrolyte are not homogeneous or isotropic. So they experience a net electric field or the net dipole moment. As a consequence of this, the ions or the free electrons present in the metal electrode move away or towards the interface depending on the direction of the electric field. Thus, charge separation across the electrode electrolyte interface give rise to interfacial potential difference. The formation of an electrified interface can be described in the following step. First of all, redistribution of the ions or the molecules of the electrolyte take place. That is followed by the charging of the electrolyte side of the interface, which produces an induction of charge on the metal side of the interface, causing the charge separation and leading to the formation of interfacial potential difference. Now, what is electrical double layer? It is basically the net orientation of dipoles and charges along with the interface region at the boundary of an electrode electrolyte interface is called an electrical double layer. So the double layer formed at the boundary have two fundamental aspects. One is electrical aspect and another one is structural aspect. In the electrical aspect, the magnitude of excess charge densities on each phase and the variation of potential with the distance from the interface is determined, while the structural aspect deals with the arrangement of particles of two planes in the interface region in order to electrify it. Now, various theories and models have been proposed to understand and develop the structure of this electrical double layer. These are Helmholtz parent model, also known as parallel plate condenser model, Goy-Chapman diffuse charge model of the double layer, Stern model, Graham model, and BDM triple layer model. These models will be discussed in detail in the upcoming slides. So, Helmholtz model is also known as parallel plate condenser model as it draws the analogy between this interfacial region and the capacitor. It was the first and the simplest model developed to understand the structure of electrical double layer. It was developed even before the discovery of electron. So this model was not able to explain the arrangement of the molecules or ions across the boundary of the interface. The model suggested that the charge on the metal ion draws out the random distribution of ions in the solution and a counter layer of charge is formed. This electrified interface consists of two sheets of charge equal in magnitude and opposite. So the potential drop between these two layers of charge is linear. So, this represents the potential difference across the plates of the condenser, where xh is the distance between these two plates, and epsilon naught are the permittivity of the dielectric constant. Qm is the charge on the surface of the metal electrode, and the capacitance is given by epsilon naught by xh. That means that it is independent of the concentration and the electrode potential. Now here we can see that the it assumes that the ions in the solution are not liberated. They are all attracted or bounded by the electrostatic force of attraction as they are feeling it from the excess of charge on the present on the surface of the metal electrode. And in this, the main reason for the failure of this model is due to the assignment of the value of the dielectric constant of the solvent in the solvent layer. As I was explaining this, Helmholtz model, as the charges are equal and opposite to the present in the to the charges present in the solution, so we can expect a linear decrease in the potential, as shown here. And this boundary has a distance xh, and this can be drawn in analogy with the two parallel plates of the capacitor. Now, the reasons for the failure of the Helmholtz model. The main reason for the failure of this model is assigning the value of dielectric constant of the solvent changes with the distance in the interface region. The model is not complete as it predicts that the capacitance is independent of concentration and potential applied to the electrode. Moreover, it was not able to explain the the curve for the differential capacitance with the potential. As shown here, this is the experimental curve that shows that it varies with the concentration. The capacitance varies with the concentration, but as we have discussed earlier, that according to Helmholtz double layer model, the capacitance is independent of the concentration. So here we get the straight line. So it does not seem to be. So we can say that the electrified interface does not seem to behave like a parallel plate condenser model. Now, in order to improve the shortcomings of the Helmholtz model, another model that is known as Goy-Chapman diffuse charge model of double layer came into existence. Unlike Helmholtz model, it does not fixes the solution charges to the arrangement that is parallel to the surface of electrode. This model liberates the ion from the sheets of the parallel to the electrode. Counter ions are not rigidly held, but they tend to diffuse into the bulk phase or the liquid phase. It assumes that the ions are point charges. Due to thermal motion of the ions, the ordering tendency induced in the interface region is perturbed. It successfully overcomes the weakness of the constant differential capacity of the electrified interface. So, as shown here, it also tells us about the thickness of the diffuse layer forms in this model, and it is given by length, that is kappa, and that depends on the concentration of ions. So the capacitance is not independent of potential and the concentration of ion according to Goy-Chapman model. As shown here, the ions are diffused in the bulk of the solution. They are not fixated due to the electrostatic force of attraction as they are feeling due to this surface of the electrode. As the charge of the ion and the ion present in the solution and that of the metal electrode is not equal and opposite to each other. So we can see the variation of potential is not linear here. It is an exponential variation of potential that can be shown here. So, what are the failures of this diffuse double layer model? One of the most important failure is that it assumes that the ions are point charges, so they can approach the surface of the electrode without any restriction of distance. But this is not so. They are also solvated. So this was one of the most important failure of this model. Another failure is the dielectric constant is assumed to be constant in the interface region, while it is not so. The model also fails to reproduce the capacitance potential curve that are known as electrocapillary curves. As shown here, this model successfully explains the electrocapillary curve at the low value of potential, as can be seen, but it fails to explain the capacity variation at higher value of potential. This is due to the capacitance catastrophe that occurs by assuming that ions are point charges. As if the ions are point charges, then they can approach the surface of the electrode to the without any restriction of distance, and so this causes the increase in capacitance without any limit. So, another model, in order to overcome the shortcomings of both these models, came into existence that is known as Stern model or stuck layer model. This model combines the Helmholtz and the Goy-Chapman model both. It takes into account the finite size of the ions. So, this model is widely accepted in the electrochemical double layer capacitors that are used in supercapacitors. So, The second modification of the Stern theory is dividing the solution charge into two charges. One is QS, that is immobilized part of the charge close to the surface of the electrode in the OHP, that is outer Helmholtz plane or compact layer. That is the assumption of, according to the Helmholtz double layer model. While QG is the charge due to the diffuse part of the due to the diffuse part or the diffuse ions present in the solution, that is assumption according to the Goy-Chapman double layer model. So we can see that the QS is equals to QH plus QG, and the potential varies linearly with distance in the inner compact layer, that is up to OHP, and decreases exponentially in the bulk region, we as shown here. So here QS is the charge that is present on the surface of the metal electrode. This is OHP, outer Helmholtz plane or the outer Helmholtz layer. Up to this, it follows a linear variation of potential as explained by Helmholtz model. And this is the diffuse layer, and this diffuse layer is due to the scattered or the scattered ions or the diffuse ions. There is an exponential variation of potential here. This layer is also known as Stern layer, as ions are fixed here and they are least solvated as compared to the ions present in the solution. So the capacitance can be given as the series, as the addition of the capacitance according to both these models, Helmholtz and Boyd-Chapman model, as shown in this formula. Now, Stern model was able to explain the electrocapillary curve much better than the Goy-Chapman model and Goy-Chapman model. So another model that came into existence was Graham model. Graham modified the concept of specifically adsorbed ions and proposed that some ionic or uncharged species can penetrate the Stern layer. Specifically, adsorbed ion can be defined as the adsorption of ions at the surface of the electrode by losing their solvation property, by forming strong bonds with the electrode. D.C. Graham proposes three regions across the electrified interface. One is inner Helmholtz plane, another one is outer Helmholtz plane, and third one is diffuse layer. The inner Helmholtz plane is the plane that passes through the locus of the centers of these specifically adsorbed ions. As I have already discussed, specifically all adsorbed ions are the desolvated ions that does not experience any solvation due to the other ions or the ions of the water molecules present in the solution. While outer Helmholtz plane passes through the locus of the center of the non-specifically adsorbed ions that are partially solvated due to the electrostatic force of attraction they feel from the ions of water molecules or or any other solution. And the third one, that is outside this OHP region, that is our outer Helmholtz plane region, is the diffuse region. So BDM model, it is known as Bockris, Devanathan, and Mullen model. It represents the solution side of the interface in the terms of triple layer. It is specifically designed for the water molecule. It uh, In this, an inner Helmholtz plane is introduced as the locus of the electrical centers of specifically adsorbed ions, as shown here. And it is this model is used to explain the orientation of the solvent molecules or the dipoles of the solvent molecules and their variation with the potential. So here this arrow represents the water dipole, and these are the solvated ions, and this charge this is the charge on the metal surface. So the charge excess of the charge on the metal surface will draw out the charge present in the solution, and will form an inner Helmholtz plane as shown here, and these ions present in the inner Helmholtz plane are completely desolvated in nature, while the other plane, that is outer Helmholtz plane, have ions that are partially solvated, and the diffuse and the diffuse region have ions that experience the solvation due to the presence of other ions, as shown here. Now, the variation of potential with distance can be shown as the linear variation up to the inner Helmholtz plane, and an exponential variation in the diffuse region. So, so these were all about the different models that were used to explain the electrified interface structure or an electrical double layer. Now this electrical double layer give rise to an electrical double layer capacitance due to the induced ions that are formed at the electrical double layer. Now electrical double layer capacitance are used in electrical devices. Basically, nowadays, electrochemical double layer capacitors, capacitance based supercapacitors are designed. The main reason is that they offer high power density and high charging and discharging cycle. These EDLC type capacitors have three things. One is two conductive electrodes. Usually, we prefer it to be made by carbon or graphite or CNT, and then these electrodes are separated by a separator and an electrolyte, you, like NaClO4 or etc. When the voltage is applied across the plates get charged. Here the voltage is, this is the charging, and this represents the discharging process. When the voltage is applied across it, the plates get charged and will draw the ions of oppositely charged ions are drawn towards it and lead to the formation of an electrical double layer. So this is the process, and so the ions will be liberated or in the free form during the time of discharging. So this was all about it.